There is a boundary in space that once crossed, nothing can return from. Not damaged, not slowed, not redirected, gone. Light itself cannot escape it. Information cannot escape it. The laws of physics as we understand them cannot fully describe what happens beyond it. And the nearest one to Earth, sitting roughly 1,560 light years away, has been there the entire time humans have existed, silently swallowing everything that gets too close. The question of what actually happens inside a black hole is not one physics has answered. It is one physics has been fighting over for more than a century, and the fight has not settled, not even close. What makes this genuinely strange, stranger than almost any other unsolved problem in science, is where the disagreement comes from. It does not come from a lack of smart people working on it. It comes from the fact that the two most tested, most reliable, most successful theories in the history of physics look at a black hole and give completely different answers, and both of them cannot be right. Every other question in science has a framework, a direction, a set of tools that, even if the answer is not yet known, can at least be pointed at the problem. Inside a black hole, those tools stop working. What happens beyond the event horizon, what time does, what matter does, what reality itself does, sits in a place where the known universe simply runs out of answers. And the explanations that physicists have proposed for what might be happening in there are some of the strangest ideas in all of science. Tonight, we go to the edge of what physics actually knows and find out what waits on the other side of it. If questions that sit at the edge of human understanding are why you watch, subscribe, and leave a like, it helps this reach someone else who would want to think about it. And drop a comment. Does it unsettle you that the two best theories in physics completely contradict each other inside a black hole? Let's begin with the boundary where the known universe stops giving us answers. Long before we understood black holes, we understood falling. Apples fell, rain fell, moons circled planets because gravity held them there. Every object in the universe pulls on every other object, quietly shaping motion across enormous distances. Even your body bends space-time slightly. The effect is just too small to notice. A black hole begins with the same force. Nothing new is added. Gravity simply becomes overwhelming. Most people imagine a black hole as an empty tear in space, a kind of cosmic drain. But it is not a hole in the ordinary sense. It is an object, an extreme concentration of mass compressed into a region so dense that escape itself becomes impossible. To understand why, we need escape velocity, the speed required to break free from gravity forever. On Earth, that speed is 11.2 kilometers per second. For the Sun, it rises to 617 kilometers per second. Massive objects demand faster escapes because their gravity curves spacetime more severely around them, but there is a limit. Light travels at 299,792 kilometers per second, the fastest speed anything can achieve. If an object becomes dense enough that escaping its gravity would require moving even faster than light, then nothing can leave. Not particles, not signals, not time-stamped messages from the inside. That threshold is called the Schwarzschild radius, named after physicist Carl Schwarzschild, who calculated it in 1916 while serving on the Eastern Front during the First World War. Any mass compressed within this critical radius becomes a black hole. Earth would need to shrink to roughly the size of a marble. The Sun would need to collapse into a sphere only about 3 kilometers wide. Black holes appear in several forms. Stellar black holes form after massive stars die and collapse inward under their own gravity. Supermassive black holes sit inside most galaxies, including our own Milky Way, reaching millions or billions of solar masses. Their origin remains uncertain. Between these extremes are intermediate black holes, the missing middle category astronomers are still trying to confirm in large numbers. Around every black hole lies the event horizon. This is the true boundary, not a surface, not a shell, just a mathematical line in spacetime beyond which every possible path leads deeper inward. Once crossed, return becomes physically impossible, but the crossing itself may feel strangely ordinary. If the black hole is large enough, you could drift through the event horizon without sensing any sudden change. No impact, no flash, no visible border floating in darkness. The catastrophe waits further inside, and this is where physics begins to fracture. Einstein's general relativity describes gravity beautifully across stars, galaxies, and the expanding universe. Quantum mechanics governs atoms, particles, and the hidden uncertainty beneath reality itself. Both theories work extraordinarily well, but inside black holes, they collide. Their equations no longer agree. At the center of a black hole, our understanding of the universe stops speaking with one voice. Deep inside every star, matter spends its entire existence resisting collapse. Hydrogen nuclei fuse into helium under crushing pressure, releasing enormous energy in the process. That energy pushes outward as radiation and heat, while gravity presses inward from every direction at once. For millions or billions of years, the balance holds. A star survives because these forces remain almost perfectly matched, but stars are temporary negotiations. As fusion continues, heavier elements begin forming in layers around the core. Helium becomes carbon, carbon becomes oxygen. In the most massive stars, the chain continues until iron appears at the center. Iron changes everything. Unlike lighter elements, iron fusion consumes energy instead of releasing it. The engine stalls. A star at least 20 times the mass of our Sun cannot survive this moment for long. The outward pressure vanishes almost instantly. Gravity no longer meets resistance. The core collapses inward in less than a second, reaching velocities so extreme that matter falls at roughly 70,000 kilometers per second, nearly 23% of light speed. Temperatures surge into billions of degrees. Atomic structure disintegrates under the compression. Then the collapse rebounds. The infalling outer layers strike the compressed core and explode outward in a supernova, one of the brightest events in the universe. For weeks, a single dying star can outshine a galaxy containing 200 billion suns. Heavy elements forged during the explosion scatter across interstellar space, mixing into future stars, planets, and eventually living cells. But the center keeps falling. In 1931, physicist Subramanian Chandrasekhar calculated a critical threshold for dying stars. If the remaining core contains less than roughly 1.4 solar masses, electron pressure, a quantum effect produced by tightly packed electrons, can halt the collapse. The star stabilizes as a white dwarf, dense but intact. Above that limit, gravity wins permanently. The collapse accelerates beyond every known form of resistance. Electrons merge with protons, atomic identities disappear. Matter compresses beyond neutron star density, toward a state our equations can no longer properly describe. General relativity predicts a singularity, a region where density approaches infinity and spacetime curvature becomes unbounded. But nature does not provide a visible transition. There is no cosmic flash announcing the birth of a black hole. Once the collapsing mass contracts within its Schwarzschild radius, the event horizon forms quietly around it. Light can no longer escape. The star simply vanishes from direct view, leaving only gravity shaping the surrounding darkness. Some stellar black holes discovered in recent years approach 100 solar masses. Their existence surprised astronomers because standard stellar evolution models struggle to produce remnants that large. Certain theories suggest unusually low metal content in ancient stars may reduce mass loss before collapse. Others point toward mergers between smaller black holes inside dense star clusters. For now, the exact mechanism remains uncertain. What we do know is simpler and stranger. A star spends most of its lifetime preventing collapse. Then one day, the resistance ends. Gravity finishes the sentence. If you could drift beside a black hole long enough, you would never see the boundary itself. There is no surface suspended in space, no swirling gate, no visible edge separating safety from catastrophe. The event horizon exists only as geometry, a precise location where escape ceases to be possible. You could move through it without touching anything at all, but its scale changes dramatically with mass. At the center of the Milky Way sits Sagittarius A star, the supermassive black hole around which our galaxy slowly turns. Its event horizon stretches roughly 12 million kilometers from the center, wider than the diameter of the Sun itself. A stellar black hole weighing 10 solar masses is far smaller. Its event horizon spans only about 30 kilometers across, compact enough to fit comfortably inside a city. Just outside this boundary lies another strange region, the photon sphere. This is the zone where gravity bends light into complete circles. A photon, a particle of light traveling at exactly the correct angle, could orbit endlessly around the black hole, like a moon around a planet. The photon sphere forms at 1.5 times the Schwarzschild radius, creating a shell where spacetime curvature becomes almost impossible to intuit. Nothing stable lasts there for long. The event horizon behaves like a one-way membrane because causality itself changes shape nearby. Causality is the structure determining which future events remain physically reachable. Outside the horizon, you can still choose among many possible directions through space. Inside it, every possible future path points inward, not because something pulls you like a rope, but because spacetime no longer contains routes leading outward. The geometry closes behind you. From far away, though, the story appears entirely different. A distant observer watching someone fall toward the horizon would never actually see them cross it. As gravity intensifies, time dilation becomes extreme. Time dilation means clocks run at different rates depending on gravity and motion. Near the horizon, the falling person's clock appears to slow dramatically compared with clocks far away. Their movements gradually fade. Light escaping from their body loses energy climbing out of the gravitational well. Its wavelength stretches longer and redder, a process called gravitational redshift. Seconds appear to lengthen into minutes, minutes into years. The image dims continuously, freezing ever closer to the boundary without quite disappearing. Their final visible moment lingers indefinitely, stretched thin across the future of the universe. But the falling person experiences none of this slowing. Their heartbeat feels normal. Their thoughts arrive at ordinary speed. They continue downward without witnessing their own clock distort. Crossing the event horizon produces no sudden sensation, no visible crack in space, no violent impact announcing the transition. One moment escape remains possible. The next, every path leads deeper inward. The universe outside still exists above them, but it has become unreachable forever. Stand near the ocean long enough, and you can watch gravity pull water across an entire planet. The moon raises tides because its gravitational pull is slightly stronger on the side of Earth facing it than on the far side. That difference is called a tidal force. the variation in gravity across the length of an object. On Earth, the effect is gentle. Seas rise a few meters, coastlines slowly breathe inward and outward beneath the night sky. Near a black hole, the same principle becomes lethal. As you fall toward a stellar black hole, gravity gripping your feet grows dramatically stronger than gravity pulling on your head. The difference can reach billions of times Earth's surface gravity before you ever approach the event horizon. Space itself becomes uneven across the length of your body. The stretching begins gradually. First, your body elongates along the vertical direction, pulled toward the center by increasingly unequal forces. At the same time, gravity compresses you sideways. Your chest narrows, your arms draw inward. The process accelerates continuously because every meter downward increases the gravitational difference further. There is no stable stage. Bones separate at the joints. Internal organs distort beyond biological limits. Molecular bonds, the electromagnetic attractions holding matter together, begin to fail under the stress. Proteins unravel. Cells rupture apart into individual molecules. Soon, even the molecules cannot survive. Atoms lose their electrons, stripped away into plasma by the violence of the surrounding field. Gravity keeps tightening. Eventually, protons and neutrons themselves are torn from their arrangements inside atomic nuclei. Matter loses all recognizable structure. The distinction between solid objects and compressed particle streams disappears entirely. According to general relativity, the collapse continues toward conditions where our current physics stops giving reliable answers, but scale changes the experience in surprising ways. A supermassive black hole behaves differently because its event horizon is enormously large. Near Sagittarius A star, the gravitational variation across a human body at the horizon would be relatively small. You could cross the boundary intact without immediate tidal destruction. The fatal stretching would occur much deeper inside, where space-time curvature intensifies closer to the center. Astronomers have watched this process happen to stars. These events are called tidal disruption events, moments when a wandering star passes too close to a supermassive black hole and begins to unravel under tidal forces. As the star stretches apart, enormous streams of stellar material spiral around the black hole, heating to extreme temperatures and releasing brilliant bursts of radiation visible across billions of light years. One of the clearest examples appeared in 2019. Astronomers detected an event named AT 2019 KIS, located roughly 215 million light years from Earth. For the first time, telescopes captured the destruction in remarkable detail, tracing how the star's material formed luminous outflows and expanding debris clouds as the black hole consumed it piece by piece. What we saw was not an explosion in the ordinary sense. It was gravity pulling matter beyond the limits of form itself. A clock carried to the top of a mountain will not agree perfectly with one left at sea level. The difference is tiny, almost absurdly small, but measurable. Gravity alters the passage of time itself. According to Einstein's general relativity, clocks deeper inside a gravitational field tick more slowly than clocks farther away. Time is not separate from gravity, it is shaped by it. We already rely on this effect every day. GPS satellites orbit roughly 20,000 kilometers above Earth, where gravity is slightly weaker than on the surface below. Their onboard atomic clocks gain about 38 microseconds each day compared with clocks on Earth. A microsecond is 1/1,000,000th of a second. That sounds insignificant. But without constant relativistic corrections, GPS positioning errors would accumulate by nearly 10 kilometers per day. Your phone works because Einstein was correct. Near a black hole, the distortion becomes almost impossible to imagine. Around Sagittarius A star, time slows so severely near the event horizon that 1 year experienced close to the boundary could correspond to roughly 4,000 years passing for someone far away. The exact ratio changes with distance because gravity does not switch abruptly from weak to strong. It deepens continuously as you descend inward. But nothing feels different locally. Your pulse remains steady. Your thoughts arrive normally. A second still feels like a second because your brain, body, and measuring devices are all moving through the same warped spacetime together. Time dilation only becomes visible when two observers compare clocks after following different paths through gravity. This idea entered popular culture through the film Interstellar. In the story, astronauts visit a planet orbiting near a fictional black hole called Gargantua. A few hours on the planet correspond to decades passing elsewhere. The scene was dramatized for cinema, but the underlying mathematics came from real physics. Physicist Kip Thorne served as scientific advisor during production, helping ground the depiction in relativistic equations rather than fantasy. The emotional weight came from reality itself. If you traveled close enough to a black hole and later returned, you would find the outside universe profoundly changed. Civilizations could rise and vanish while only months passed for you. Languages would evolve. Continents might shift. Entire generations could live and die during what felt like a brief detour through stronger gravity. And neither perspective would be more correct than the other. This is the quiet strangeness hidden inside relativity. Two people can inhabit the same universe while experiencing radically different amounts of time simply because gravity carried them along different routes through spacetime. The universe does not contain one universal clock governing everything equally. Time behaves more like geography. It bends around mass, stretches near gravity, and flows unevenly across the cosmos. Black holes simply reveal the curvature in its most extreme form, exposing that what we experience as a steady forward motion is part of the structure of spacetime itself. At the center of a black hole, the equations stop behaving like descriptions of nature and begin behaving like warnings. General relativity predicts that all the mass collapsing inward continues compressing without limit. Volume shrinks toward zero, density rises toward infinity, space-time curvature becomes unbounded. This predicted endpoint is called the singularity, a region where the mathematics no longer produces physically meaningful answers. In physics, infinity is usually a sign of failure. When an equation gives an infinite result for a real quantity, physicists rarely conclude that nature literally contains infinities. More often, it means the theory has reached conditions beyond its ability to describe accurately. The singularity may not be an actual object hidden inside black holes. It may instead mark the place where our current understanding breaks apart. The scale involved is unimaginably small. Modern physics contains a fundamental unit called the Planck length, approximately 1.616 times 10 to the negative 35 meters. Below this distance, our familiar concepts of space and geometry cease functioning properly. Quantum uncertainty becomes so extreme that space-time itself may fluctuate violently, losing any smooth structure. The singularity lies beyond this boundary. General relativity treats spacetime as continuous and smooth, but quantum mechanics suggests reality becomes grainy and probabilistic at sufficiently tiny scales. Inside a black hole, both descriptions are pushed into direct conflict. Neither theory can fully dominate the conditions there. In 1965, mathematician and physicist Roger Penrose proved something deeply unsettling. Using only Einstein's equations, Penrose demonstrated that once an event horizon forms under realistic conditions, a singularity becomes mathematically unavoidable. The collapse cannot stabilize or reverse within classical relativity. Space-time itself must terminate in some extreme state beyond the reach of the theory. This work transformed black holes from speculative curiosities into serious physical predictions. It later contributed to Penrose, receiving the 2020 Nobel Prize in Physics. But rotating black holes complicate the picture. Most real black holes spin because the stars that formed them rotated before collapse. These are called Kerr black holes, named after mathematician Roy Kerr, who solved the rotating equations in 1963. In Kerr geometry, the singularity is not a point. It forms a ring, an infinitely thin loop of compressed spacetime. The mathematics surrounding this ring becomes extraordinarily strange. Certain theoretical paths appear to avoid direct collision with the singularity itself, potentially continuing into other regions of spacetime. Some solutions resemble tunnels connecting distant locations or entirely separate universes, but these possibilities emerge from idealized equations under conditions likely disrupted by quantum effects and instability. No evidence confirms such interiors physically exist, and so we arrive at an unusual boundary in science. We can describe the gravitational behavior surrounding black holes with extraordinary precision. We can predict orbital motion, lensing effects, and the shape of spacetime outside the horizon. But at the center, our most successful theory produces its own collapse. The singularity is where physics stops explaining reality and begins admitting ignorance. For decades, black holes seemed absolute. Matter could fall inward. Light could vanish permanently. Nothing escaped once the event horizon formed. Black holes appeared to be the final storage vaults of the universe, objects that only grew larger as they consumed surrounding material. Then, in 1974, Stephen Hawking reached a conclusion that overturned the entire picture. Black holes are not eternal. The calculation emerged from an uneasy combination of quantum mechanics and curved spacetime. Quantum theory predicts that empty space is never truly empty. Even the vacuum flickers with activity. Tiny particle pairs constantly appear and disappear everywhere throughout the universe. One particle carries positive energy, the other carries negative energy. Normally, they annihilate each other almost immediately, leaving no lasting trace. Near an event horizon, the geometry changes the outcome. If one of these particle pairs forms exactly at the boundary, gravity can separate them before annihilation occurs. The negative energy particle falls inward across the horizon, while the positive energy particle escapes into space as real radiation. To conserve total energy, the black hole loses a small amount of mass each time this happens. This escaping glow is called Hawking radiation. Over immense stretches of time, the process slowly drains the black hole itself. The event horizon contracts, the mass decreases. Eventually, given enough time, the black hole evaporates entirely. But the timescales are staggering. A stellar black hole containing 10 solar masses would require roughly 2 times 10 to the 67 years to disappear completely. The current age of the universe is only about 13.8 billion years. Compared with black hole evaporation, all recorded cosmic history so far occupies barely the first instant of an unimaginably longer future. Smaller black holes behave differently. The temperature of Hawking radiation increases as black hole mass decreases. Large black holes radiate extremely weakly, colder than the surrounding cosmic microwave background. Tiny black holes become hotter and evaporate much faster. Hypothetical primordial black holes, if formed during the violent density fluctuations of the early universe, may already have vanished long ago in brief flashes of intense radiation. As evaporation accelerates, the final stage could become catastrophic. A shrinking black hole radiates faster and faster, releasing enormous bursts of high energy particles during its final moments. The last fraction of a second may unleash more energy than millions of nuclear weapons combined, concentrated into a region smaller than an atom. Yet no telescope has directly observed Hawking radiation. The predicted signal from known black holes is far too faint, buried beneath the ambient radiation filling space itself. Even so, the theory remains deeply respected because it emerges naturally from combining well tested principles of quantum theory and relativity. And it creates a disturbing problem. If black holes can evaporate away completely, then everything that fell inside eventually disappears with them: stars, planets, radiation, information itself. Quantum mechanics insists information cannot truly be destroyed, but Hawking radiation appears random, carrying no obvious record of what entered the black hole. For the first time, black holes threatened not only matter and light, but the foundations of physics itself. Burn a book, and the words seem gone forever. The pages blacken, ink dissolves into ash, smoke, and heat. But according to quantum mechanics, the information describing the original book is not destroyed. If you could measure the exact quantum state of every particle released during the fire, every photon, every drifting molecule, every collision in the air, the process could theoretically be reversed. The universe keeps records. This principle sits deeply inside modern physics. Quantum systems evolve in ways that preserve information, even when the original arrangement becomes hopelessly scrambled. Disorder increases, accessibility vanishes, but the underlying information remains embedded somewhere within the evolving state of matter and energy. Black holes appear to violate this rule completely. When matter crosses the event horizon, all details describing it seem trapped forever beyond observation. The exact arrangement of particles, spins, charges, and quantum states disappears from the accessible universe. Then Hawking radiation slowly evaporates the black hole away, releasing radiation that appears entirely random. Nothing recognizable returns. If the black hole eventually vanishes completely, the information describing everything that fell inside seems erased from existence itself, not hidden, destroyed. And quantum mechanics does not permit that outcome. For decades, Stephen Hawking argued that information truly was lost inside black holes. Many physicists found the conclusion deeply disturbing because it implied that one of the most successful frameworks in science breaks under gravitational collapse. The disagreement became famous. In 1997, Hawking made a public bet with physicist John Preskill regarding whether information survives black hole evaporation. 7 years later, in 2004, Hawking conceded. During a conference in Dublin, he handed Preskill an encyclopedia of baseball, joking that information can always be recovered, though perhaps not in the original form. But the actual solution remains uncertain. One influential proposal is called black hole complementarity, developed largely by physicist Leonard Susskind. The idea suggests that information behaves differently depending on the observer. From far away, information never truly enters the black hole. Instead, it becomes encoded across the event horizon and slowly leaks outward through Hawking radiation over immense spans of time. For the falling observer, though, nothing special occurs at the horizon. The information continues inward normally. Both descriptions remain valid simultaneously because no observer can witness both versions at once. Reality preserves consistency, by preventing direct contradiction between perspectives. This argument led toward an even stranger concept, the holographic principle. According to this idea, all information describing a three-dimensional region of space may actually be encoded on its two-dimensional boundary, much like a hologram storing depth on a flat surface. If true, the universe may be fundamentally informational at its deepest level, and black holes forced physicists to consider that possibility seriously. The information paradox remains unresolved today, not because scientists ignored it, but because every attempted answer reshapes our understanding of space, gravity, and reality itself. In theoretical physics, the most dangerous discoveries often begin as attempts to fix older problems. By 2012, many researchers believed the information paradox might eventually yield to some refined understanding of black hole evaporation. The debate remained unsettled, but promising ideas existed. Then four physicists, Ahmed Almhiri, Donald Marolf, Joseph Polchinski, and James Sully, published a paper that disrupted nearly every proposed resolution at once. The group became known simply as AMPS. Their argument focused on quantum entanglement, the phenomenon where particles become linked so completely that measuring one instantly constrains the state of another, regardless of distance. Entanglement obeys strict mathematical rules. One of them is called monogamy of entanglement, meaning a quantum system cannot be fully entangled with two independent systems simultaneously. That detail created a catastrophe. If Hawking radiation carries information away from a black hole, then outgoing particles must somehow remain entangled with the information still associated with the black hole interior. But according to standard quantum theory, newly emitted Hawking particles are already entangled with partner particles behind the horizon. Both conditions cannot remain true together. Something fundamental had to fail. Either quantum mechanics breaks under these conditions, allowing information destruction after all, or Einstein's equivalence principle collapses at the event horizon. The equivalence principle states that a freely falling observer should experience local physics normally, without detecting anything unusual at the horizon itself. AMPS showed that preserving quantum information appears to destroy that smooth passage. Instead of empty space-time near the horizon, the mathematics predicts an intense barrier of high-energy radiation, a firewall capable of annihilating anything attempting to cross. A person falling toward a sufficiently massive black hole would not drift peacefully inward. They would be incinerated instantly at the boundary itself. The event horizon would become violent. This conclusion shocked physicists because it overturned decades of intuition surrounding black holes and relativity. The AMPS paper did not solve the information paradox. It demonstrated that previously accepted solutions generated an even deeper contradiction between gravity and quantum theory. The crisis still remains unresolved. One speculative response emerged the following year from physicists Juan Maldacena and Leonard Susskind. They proposed an idea summarized by the phrase ER equals EPR. ER refers to Einstein-Rosen bridges, another name for wormholes. EPR refers to entangled particles, named after Einstein, Podolsky, and Rosen. The proposal suggests these phenomena may actually be connected. Entangled particles could be joined through microscopic wormholes embedded within spacetime itself. If true, the outgoing Hawking radiation might remain geometrically connected to the black hole interior, preserving information without violating quantum rules or creating destructive firewalls. No experimental evidence confirms this picture, but the possibility changed the conversation. Black holes were no longer only about gravity crushing matter. They became clues, suggesting that space-time, quantum entanglement, and the structure of reality itself may emerge from something deeper still. For centuries, black holes existed only as equations written on paper. Astronomers tracked stars moving around unseen masses. Physicists mapped warped spacetime using mathematics alone. Radio telescopes detected violent energy pouring from galactic centers. But no human being had ever directly seen the silhouette of a black hole itself. That changed on April 10th, 2019. The image did not come from a single observatory. It emerged from the Event Horizon Telescope, a coordinated network of 8 radio observatories spread across 4 continents, from Antarctica to Hawaii to the mountains of Chile. Using a technique called very long baseline interferometry, the telescopes synchronized their observations with atomic clocks so precisely that the entire planet effectively became one Earth-sized instrument. The target lay 55 million light-years away. At the center of the giant galaxy, Messier 87 sits, Messier 87 star, a supermassive black hole containing roughly 6.5 billion solar masses. Capturing its shadow required extraordinary resolution, equivalent to reading a newspaper in New York while standing in a cafe in Paris. Even Earth's diameter barely provided enough precision. After years of observation, calibration, and data processing, the image finally appeared. A glowing asymmetric ring of orange light surrounded a dark central region. The bright material was the accretion disk, superheated gas orbiting at relativistic speeds before falling inward. The darkness at the center was the black hole's shadow, the visible imprint of spacetime bent so severely that light itself vanished from view. But the ring was uneven. One side appeared brighter because material rotating toward Earth experienced relativistic beaming, a consequence of Doppler effects occurring near light speed. Motion itself altered the brightness of the surrounding plasma, and the shadow was larger than expected intuitively. What we see is not the event horizon directly, but the photon sphere surrounding it, where gravity bends light into unstable orbits before either escape or capture. This magnified the apparent shadow to roughly 2.5 times the diameter of the event horizon itself. Then, on April 10th, 2022, another image arrived. This time the target was Sagittarius A star, the black hole at the center of our own galaxy. Although far closer than M87 star, it proved more difficult to image because the surrounding gas changes rapidly. Material near Sagittarius A star completes orbits in minutes rather than days, causing the image to flicker continuously during observation. Reconstructing these images required entirely new computational methods. Katie Booman, then a graduate student, helped develop the CHIRP algorithm used to process the sparse radio data into coherent images. Her work became a visible symbol of the global collaboration behind the project, involving hundreds of researchers across physics, astronomy, engineering, and computer science. What emerged from all this effort was not merely a photograph. It was a test of general relativity under extreme conditions. The size and shape of the observed shadow matched Einstein's predictions within measurement, uncertainty. More than a century after proposing spacetime curvature, the equations still described reality with astonishing accuracy. Every night, above the dense star fields of Sagittarius, something invisible anchors the Milky Way together. You cannot see it with your eyes. Dust clouds block the galactic center from ordinary visible light. But 26,000 light-years away, at the exact rotational heart of our galaxy, a supermassive black hole waits in silence. Astronomers call it Sagittarius A star. It has been there for all of human history. The object contains roughly 4.15 million times the mass of our Sun, compressed into a region smaller than Mercury's orbit. Yet the black hole itself emits no light. What revealed its existence were the stars moving around it. Near the galactic center orbits a crowded cluster called the S stars. These stars travel at extraordinary velocities, tracing tight elliptical paths around an unseen point in space. One of them, S2, became especially important. It completes a full orbit every 16 years and reaches speeds near 7,650 kilometers per second at closest approach, roughly 2.6% of light speed. Nothing ordinary could hold stars that fast. For decades, astronomers Andrea Ghez and Reinhard Genzel tracked these motions using infrared telescopes capable of seeing through the dust toward the galactic core. Year after year, they watched the stars curve around empty space, following paths dictated by a massive invisible object concentrated into an impossibly small region. Their observations provided the strongest evidence yet for a supermassive black hole inside the Milky Way. In 2020, Ghez and Genzel shared the Nobel Prize in Physics with Roger Penrose for this work. But Sagittarius A star appears strangely quiet today. Its accretion disk contains relatively little matter. Compared with the luminous quasars observed in distant galaxies, our central black hole is almost dormant. It consumes only sparse gas and dust drifting too close to escape. Evidence suggests this calm state is temporary. Roughly 2 million years ago, Sagittarius A star may have entered a far more active phase, feeding rapidly and releasing enormous jets of energy from the galactic center. Astronomers discovered traces of this ancient activity in structures called the Fermi bubbles, two immense lobes of gamma ray emitting gas extending approximately 25,000 light-years above and below the Milky Way's plane. The bubbles still glow today. Their existence raises a subtle question about Earth's history. The timing overlaps loosely with early hominid evolution. Some researchers have wondered whether increased galactic radiation may have influenced atmospheric chemistry or biological conditions on ancient Earth, though no evidence currently demonstrates a direct connection. Fortunately, Sagittarius A star poses no danger to us now. At 26,000 light-years away, its gravitational influence on the solar system is negligible. The Sun orbits the galactic center once every 225 to 250 million years, completing what astronomers call a galactic year. Right now, we are simply passing through another small arc of that enormous journey. Look outward far enough, and almost every major galaxy reveals the same hidden architecture. At the center sits a supermassive black hole. Some contain only a few million solar masses. Others grow into objects so enormous that ordinary intuition stops functioning. These giants shape entire galaxies while occupying regions smaller than planetary systems. And no one fully understands how they formed so quickly after the universe began. One of the largest known examples is TON 618, a quasar located roughly 10.4 billion light-years away. At its center lies a black hole containing an estimated 66 billion solar masses. Its event horizon radius extends about 1,300 times farther than the distance between Earth and the Sunday. The scale becomes difficult to picture. If TON 618 replaced our Sun, its event horizon would engulf the entire planetary system far beyond Neptune. Yet even objects this immense appear common throughout cosmic history. That creates a serious problem. Stellar black holes form from collapsing stars, But supermassive black holes cannot simply grow through ordinary feeding over time. There has not been enough time since the Big Bang for repeated accretion alone to build billions of solar masses at the rates astronomers observe. The universe appears to have produced these giants far too early. Several ideas compete to explain this. One hypothesis proposes direct collapse black holes, enormous clouds of primordial hydrogen collapsing almost immediately after the first stars formed, bypassing normal stellar evolution entirely. Instead of producing individual stars first, entire regions of gas may have fallen inward directly into massive seed black holes. Another possibility involves dense early star clusters. Thousands of stellar black holes could have merged rapidly through repeated collisions in crowded environments, producing increasingly larger objects over relatively short cosmic timescales. But no model fully explains all observed data yet. At the same time, galaxies themselves appear strangely connected to the black holes inside them. Astronomers discovered a pattern called the M-sigma relation, a remarkably tight correlation between the mass of a galaxy's central black hole and the random velocities of stars throughout the galactic bulge. Those stars orbit thousands of light years from the black hole, far beyond its direct gravitational dominance. Yet the relationship persists across the universe. Something links galactic evolution to black hole growth with extraordinary precision, as though both structures regulate one another continuously over billions of years. The exact mechanism remains uncertain, but energy released from active black holes likely influences how gas cools, collapses, and forms new stars. When these giants actively feed, they become quasars. Quasars are the brightest sustained objects known, powered by superheated accretion disks radiating enormous energy as matter spirals inward. Some outshine entire galaxies by factors of hundreds or thousands. One especially distant quasar, J0313-1806, existed only 670 million years after the Big Bang. Yet its central black hole already contained roughly 1.6 billion solar masses. The timeline barely makes sense. The early universe appears to have produced gigantic black holes almost immediately after the first cosmic structures emerged. Instead of growing slowly alongside galaxies, they may have helped shape the universe from the very beginning. At 5:51 in the morning, Eastern Time, on September 14th, 2015, space-time itself trembled. The disturbance lasted only 0.2 of a second. No human being felt it directly. The motion crossing Earth was smaller than the width of an atomic nucleus. But inside two enormous observatories in the United States, lasers recorded a signal unlike anything ever detected before. The universe had spoken through gravity. The instruments belonged to LIGO, the Laser Interferometer Gravitational Wave Observatory. One detector stood in Livingston, Louisiana. The other sat nearly 3,000 kilometers away in Hanford, Washington. Each facility contained two vacuum tunnels arranged in an L shape, stretching 4 kilometers long. Laser beams traveled back and forth through the tunnels, measuring minute changes in distance with extraordinary precision. The recorded shift was almost impossibly small. LIGO detected a distortion equal to roughly 1,000th the diameter of a proton across the full length of its laser arms. It remains among the most precise measurements ever achieved by human technology. The source lay far beyond the Milky Way. Two black holes, one containing 29 solar masses and the other 36, had spiraled together and collided roughly 1.3 billion light-years from Earth. During their final moments, they orbited each other hundreds of times per second, accelerating until the surrounding space-time rippled violently outward. These ripples are called gravitational waves. In 1916, shortly after completing general relativity, Albert Einstein predicted that accelerating massive objects should generate waves traveling through spacetime itself, much like disturbances spreading across water after a stone falls into a pond. But for most of the 20th century, physicists doubted such waves could ever be measured directly. The effect seemed too weak. Yet the merger released astonishing energy. In the final fraction of a second, more power radiated away as gravitational waves than all the stars in the observable universe emitted as light during the same interval combined. Three solar masses converted directly into gravitational energy and spread across the cosmos at light speed. By the time the signal reached Earth, the distortion was tiny, but it carried a recognizable shape. The frequency and amplitude rose rapidly before stopping abruptly, producing a short ascending chirp. When researchers compared the waveform against Einstein's equations, the agreement was nearly exact. The signal became known as GW150914. For the first time, humanity directly confirmed that black holes merge, that gravitational waves exist, and that spacetime behaves dynamically under extreme gravity exactly as general relativity predicts. Since then, the detections have continued. More than 90 gravitational wave events have now been cataloged, including collisions between black holes and neutron stars occurring hundreds of millions or even billions of light years away. Astronomers no longer observe the universe using light alone. We have begun listening to motion itself. In 2017, Kip Thorne, along with Rainer Weiss and Barry Barish, received the Nobel Prize in Physics for helping make this discovery possible. The universe had gained a new sense through which it could be understood. Imagine releasing yourself toward a supermassive black hole with no rockets firing, no resistance beneath you, no atmosphere to push against your skin. You would feel weightless. This follows from Einstein's equivalence principle, the idea that free fall and the absence of gravity are locally indistinguishable experiences. An astronaut orbiting Earth feels weightless not because gravity disappeared, but because both astronaut and spacecraft are falling together through curved spacetime. The same principle applies near a black hole. As long as tidal forces remain small, your body notices nothing unusual. For a sufficiently massive black hole, crossing the event horizon itself would produce no physical shock, no barrier forms in front of you, no invisible membrane tears apart your spacecraft. The horizon remains a mathematical boundary, not a material surface floating in space. But the sky begins changing long before you reach it. Gravity bends incoming light more severely as you descend inward. Stars behind you appear distorted into arcs and rings. The visible universe above gradually compresses into a smaller region overhead, while darkness spreads outward around it. Space itself redirects the paths light can take toward your eyes. The deeper you fall, the narrower the visible opening becomes. Near the horizon, nearly all light from the outside universe concentrates into a bright circular ring directly above you. Photons arriving from every direction in external space become squeezed into a thin cone by the black hole's geometry. Galaxies, stars, and the fading glow of distant cosmic structure compress together overhead into a brilliant, narrowing halo. Then you pass the horizon. Nothing announces the crossing locally. Your clock still ticks normally. Your breathing remains steady, but the structure of space-time has changed in a profound way. Outside the event horizon, you can still choose among different futures. You may move left, right, upward, or away. Inside the horizon, every future points toward the singularity. Not because some force drags you there mechanically, but because the geometry itself no longer contains trajectories leading outward. The singularity stops being merely a destination in space. Inside the black hole, it behaves more like a moment in time waiting ahead of you, and time moves only forward. Escaping the singularity would resemble escaping tomorrow. Relativity predicts that your remaining lifespan depends almost entirely on the black hole's mass. Inside a stellar black hole, the distance between horizon and singularity is small. Even falling at light speed, you would survive only milliseconds after crossing inward. A supermassive black hole stretches that interior region enormously. With tidal forces temporarily gentle, you might continue falling for hours before reaching the center. Inside TON 618, the giant quasar black hole discussed earlier, the descent could theoretically last close to a week, according to your own clock. During that final interval, the external universe would remain visible only through the shrinking ring above you, growing smaller as the interior geometry carried every possible future path deeper into space-time curvature, from which no observation has ever returned. Physicists sometimes draw impossible places in order to think about them clearly. One of the most useful tools for this is the Penrose diagram, a compressed map of space-time that squeezes infinite distances and times into a finite picture. Developed by Roger Penrose in the 1960s, these diagrams allow researchers to trace which events can influence one another inside curved spacetime. They reveal structure hidden beneath equations. In the Penrose diagram for a non-rotating Schwarzschild black hole, the singularity appears not as a point, but as a horizontal boundary stretching across the future. Every possible path inside the event horizon curves upward toward it. Once crossed inward, all trajectories terminate there eventually, regardless of direction or speed. The geometry leaves no alternatives. But real black holes almost certainly rotate. Stars spin before collapse, and conservation of angular momentum preserves that rotation afterward. A rotating black hole follows a different solution to Einstein's equations called Kerr geometry, named after mathematician Roy Kerr. Its interior becomes dramatically stranger. Instead of containing only one horizon, a Kerr black hole possesses two. The outer boundary resembles the familiar event horizon already discussed. Deeper inside lies another surface called the Cauchy horizon, where predictability itself begins to fail mathematically. Between these boundaries sits the ergosphere. The ergosphere forms outside the outer event horizon because the black hole's rotation drags space-time around with it, an effect called frame dragging. The twisting becomes so extreme that nothing inside the ergosphere can remain stationary relative to distant space. Even light must rotate along with the black hole's spin. Space-time itself begins moving. This region permits a remarkable theoretical possibility called the Penrose process. If an object enters the ergosphere and splits into two fragments, one fragment can fall inward, carrying negative energy relative to distant observers. The second fragment may then escape outward with more energy than the original object possessed before entering. The extra energy comes from the black hole's rotation. In principle, rotational energy can be extracted directly from space-time geometry itself. Some astrophysicists suspect related mechanisms help power the enormous relativistic jets observed around active galactic nuclei. But the deeper interior remains uncertain. The inner Cauchy horizon appears mathematically unstable. Tiny disturbances falling inward may become amplified enormously near this boundary, potentially generating catastrophic energy densities. Many physicists suspect quantum effects would transform the region into a new singular structure before any exotic passages or extended interiors could physically exist. The equations may be misleading us again. Certain idealized Kerr solutions contain bizarre possibilities, including tunnels into other regions of spacetime or paths avoiding the singularity entirely. But these solutions assume perfectly smooth conditions unlikely to survive in real astrophysical environments filled with radiation, turbulence, and quantum fluctuations. So, the true interior geometry of rotating black holes remains unresolved. General relativity predicts structures of astonishing complexity beneath the horizon, layered boundaries where causality, motion, and time behave unlike anything experienced elsewhere in the universe. Whether these strange interiors physically exist or merely reflect limitations in the mathematics remains unknown. Fold a sheet of paper in half, press two distant points together, and the shortest route between them suddenly changes. Wormholes emerged from a similar realization inside Einstein's equations. In 1935, Albert Einstein and physicist Nathan Rosen discovered that general relativity mathematically permits bridge like structures connecting separate regions of spacetime. These structures became known as Einstein Rosen bridges, though most people simply call them wormholes. At first glance, they resemble cosmic shortcuts. In the classical Schwarzschild solution for a non rotating black hole, spacetime can be extended mathematically beyond the singularity into another region entirely. One side behaves as a black hole, allowing matter inward but never outward. The opposite side behaves as a white hole, a hypothetical object that ejects matter outward while never allowing anything to enter. The bridge connects them. But the geometry contains a fatal limitation. The wormhole collapses too quickly. It pinches shut faster than light can cross from one side to the other, preventing any signal, particle, or traveler from passing through successfully. The structure exists mathematically, but not as a usable tunnel through spacetime. Traversable wormholes require something stranger. To remain open, the throat of the wormhole would need exotic matter, a form of matter possessing negative energy density. Negative energy behaves oppositely from ordinary mass under gravity, potentially resisting collapse rather than contributing to it. No confirmed example exists in nature. Certain quantum effects, such as the Casimir effect observed between closely spaced metal plates, can produce tiny regions of negative energy under laboratory conditions. But nothing remotely large or stable enough to support a traversable wormhole has ever been discovered. Still, the idea refused to disappear. In recent years, wormholes returned to theoretical physics through the ER equals EPR conjecture proposed by Juan Maldacena and Leonard Susskind. The proposal suggests that Einstein-Rosen bridges and quantum entanglement may actually describe the same underlying phenomenon viewed differently. Entangled particles appear mysteriously linked across distance. Measure one particle, and the state of the other becomes instantly constrained, regardless of separation. ER equals EPR proposes that these correlations may correspond geometrically to microscopic wormholes connecting the particles through spacetime itself. Not traversable tunnels, more like hidden connections. If correct, the implication becomes profound. Every pair of entangled particles in the universe may share a tiny, non-traversable bridge woven into the underlying structure of reality. Space-time itself might emerge from vast networks of quantum entanglement stitched together across microscopic scales. The fabric of the cosmos would no longer be fundamental. It would be built from relationships between quantum states. White holes remain equally uncertain. General relativity permits them mathematically, but no observation has ever confirmed one exists physically. Some theorists have even speculated that the Big Bang itself may have resembled a white hole, matter erupting outward from a black hole embedded within another spacetime region. For now, wormholes remain suspended between mathematics and reality, allowed by the equations yet untouched by observation. Long before stars existed, before galaxies formed spiral arms or planets cooled into stone, the universe passed through a period of astonishing density. During the first second after the Big Bang, matter and radiation filled space almost uniformly, compressed into temperatures and pressures beyond anything now found naturally. Tiny fluctuations rippled through this newborn cosmos, most dispersed harmlessly as expansion continued. But some regions may have crossed a critical threshold. If enough mass occupied a sufficiently small volume, gravity could have overwhelmed the outward pressure immediately, collapsing those regions directly into black holes without requiring stars at all. These hypothetical objects are called primordial black holes because they would have formed near the beginning of cosmic history itself. No confirmed example has ever been found, but none have been ruled out either. Their possible sizes span an extraordinary range. Some models predict microscopic primordial black holes weighing less than a gram. Others allow objects containing thousands or even hundreds of thousands of solar masses, depending on exactly when they formed during the universe's rapid early expansion. What makes them especially important is their connection to dark matter. Observations of galaxies, galaxy clusters, and gravitational lensing all reveal that ordinary visible matter accounts for only a small fraction of the universe's total mass energy budget. Roughly 27% appears to exist as dark matter, invisible material, interacting gravitationally while refusing to emit, absorb, or scatter light in detectable ways. Its true nature remains unknown. Most dark matter theories involve undiscovered particles, but primordial black holes offer a radically different possibility. Perhaps dark matter is not made from new particles at all. Perhaps much of the universe's hidden mass consists of ancient black holes formed moments after creation. Certain mass ranges remain theoretically viable. In particular, primordial black holes weighing roughly between 10 to the 20th and 10 to the 24th grams, approximately asteroid mass, could potentially account for much or even all observed dark matter without conflicting with current observational evidence. Interest in this idea increased after LIGO detected unexpectedly massive black hole mergers. Some collisions involved black holes larger than many stellar evolution models predicted naturally. Researchers began reconsidering whether a fraction of these objects might possess primordial origins rather than forming from dying stars. Astronomers continue searching indirectly. One major technique involves microlensing, carefully monitoring distant stars for temporary brightening caused when an invisible massive object passes between us and the background star. Gravity bends and magnifies the starlight briefly, revealing the hidden object's presence, even if it emits no radiation itself. These surveys have ruled out primordial black holes across several mass ranges, but important gaps remain open. If primordial black holes truly exist in significant numbers, the implications become profound. Most matter in the universe would not consist primarily of atoms or exotic particles. Instead, the cosmos would be filled with ancient gravitational relics born during the universe's first moments, dark objects older than galaxies themselves, drifting silently through intergalactic space since the beginning of time. Not everything near a black hole falls inward. Some of the most violent structures in the universe move in the opposite direction entirely, launched outward from galactic centers in narrow beams, traveling near light speed. These structures are called relativistic jets, enormous streams of plasma and radiation extending across intergalactic space for distances measured in millions of light years. They emerge from regions smaller than solar systems. The black hole itself does not fire matter outward directly. Instead, the process begins in the accretion disk, where infalling gas becomes superheated and electrically charged. Magnetic field lines thread through this rotating disk and twist around the black hole's spin axis. As spacetime itself rotates near the event horizon, the magnetic fields tighten into immense spiraling structures. The energy becomes impossible to contain. One leading explanation is called the Blandford-Snagic process, proposed in 1977 by physicists Roger Blandford and Roman Snagic. In this model, rotational energy is extracted from the black hole through magnetic fields and converted into outward accelerating plasma, moving in tightly collimated beams. The jets behave like cosmic particle accelerators. One famous example comes from M87 star, the same black hole later photographed by the Event Horizon Telescope. Its jet stretches roughly 5,000 light-years from the galactic core and was first observed in 1918 by astronomer Heber Curtis, more than a century before the black hole itself was imaged directly. Near its base, the material travels at approximately 99.9998% of light speed. Some active galaxies orient these jets almost directly toward Earth. These objects are called blazars, among the brightest sustained gamma-ray sources in the observable universe, despite lying billions of light-years away. Their brightness becomes amplified because relativistic motion beams radiation forward along the jet direction. They appear almost impossibly luminous. Observations from the Fermi Gamma Ray Space Telescope allow physicists to study how particles accelerate under extreme magnetic and relativistic conditions. Inside these jets, electrons spiral through magnetic fields while emitting enormous energies across the electromagnetic spectrum. But the jets do more than illuminate distant galaxies. Current models suggest they actively shape galactic evolution itself. As jets blast outward, they inject tremendous heat into surrounding gas clouds. Hot gas struggles to cool and collapse into new stars, suppressing star formation across entire galaxies over billions of years. This process is called active galactic nucleus feedback. Without it, many large galaxies would continue forming stars far longer than observations allow. Instead, galaxies containing massive active black holes often transition into enormous elliptical systems filled mostly with aging red stars and little fresh stellar birth. The jets regulate the balance. Black holes, once imagined merely as cosmic destroyers, now appear woven into the architecture of galaxies themselves. Through magnetic fields, relativistic plasma, and energy released from spinning spacetime, they help determine how galaxies grow, evolve, and eventually quiet into darkness across cosmic time. Modern physics rests on two astonishing achievements that refuse to coexist peacefully. General relativity describes gravity, spacetime, stars, galaxies, and the large-scale architecture of the cosmos with extraordinary accuracy. Quantum mechanics governs atoms, particles, radiation, and the microscopic behavior underlying matter itself. Separately, both theories work almost perfectly. Together, they break. Inside black holes, and during the first moments after the Big Bang, gravity becomes enormously strong across unimaginably small distances. Under these conditions, The equations of general relativity produce infinities, while quantum mechanics demands probabilistic behavior spacetime cannot easily accommodate. Something deeper must exist underneath both frameworks. Physicists call this missing theory quantum gravity, a unified description capable of explaining gravity through quantum principles. No complete version currently exists, but several major approaches attempt to describe what happens beyond the limits of present theories. One of the most famous is string theory. In string theory, fundamental particles are not dimensionless points, but tiny vibrating strings of energy existing across 10 or 11 dimensions. Different vibrational modes produce different particles, much like different notes emerging from vibrating guitar strings. Gravity appears naturally inside the framework. One particular vibration behaves like the graviton, the hypothetical quantum carrier of gravitational force. Because strings possess finite size rather than zero size, some versions of the theory suggest singularities never truly form. The collapsing matter spreads across tiny but non-zero scales, smoothing out the infinities predicted by classical relativity. Another major approach is loop quantum gravity. Instead of treating spacetime as continuous, loop quantum gravity proposes that space and time themselves come in indivisible units, called quanta of geometry. At the Planck scale, roughly 1.6 times 10 to the negative 35 meters, spacetime behaves less like a smooth fabric and more like an underlying discrete structure. Tiny building blocks of geometry replace continuity. In certain loop quantum gravity models, collapsing matter reaches a maximum possible density before rebounding outward in a process called a quantum bounce. The singularity disappears entirely because spacetime cannot compress indefinitely beyond its smallest quantum units. A third influential framework emerged in 1997 through work by Juan Maldacena. Called the AD-CFT correspondence, this duality suggests that a gravitational theory inside a curved spacetime can be mathematically equivalent to a quantum field theory existing only on its boundary without gravity at all. Two radically different descriptions become interchangeable. This idea transformed black hole research. Physicists gained new ways to study gravity using purely quantum mechanical calculations, revealing surprising links between spacetime geometry, thermodynamics, and information theory. But none of these proposals have experimental confirmation. No collider, telescope, or detector has yet reached the Planck scale where quantum gravity effects dominate directly. The mathematics remains incomplete, and competing frameworks often disagree profoundly with one another. Still, they share one remarkable conclusion. Almost all serious approaches predict that the classical singularity cannot be physically real. Infinite density likely signals not the end of reality, but the end of our current descriptions. Something else happens beyond that boundary. We simply do not know what it is yet. The farther we look into space, the farther backward we travel through time. Light does not arrive instantly. A photon leaving a distant galaxy may spend billions of years crossing, expanding space before reaching Earth. Because of this delay, astronomy becomes a form of archaeology. Every telescope peers into earlier chapters of cosmic history, and the observable universe reaches astonishing distances. Although the cosmos is approximately 13.8 billion years old, the observable radius extends roughly 46.5 billion light years in every direction. Space itself has expanded while light traveled, stretching the distances far beyond the simple age of the universe multiplied by light speed. Near that distant boundary, quasars begin appearing. These luminous objects reveal supermassive black holes already active when the universe remained extraordinarily young. We observe them not as they exist today, but as they existed less than 1 billion years after the Big Bang. One of the most extreme examples is J0313 1806. This quasar possesses a redshift of 7.64, meaning its light began traveling toward us when the universe was only about 670 million years old. Yet the black hole powering it already contained approximately 1.6 billion solar masses. That timeline should barely be possible. Standard models struggle to explain how such enormous black holes formed and grew so quickly after the first stars emerged. Even under aggressive feeding conditions, there seems insufficient time to build structures this massive through ordinary accretion alone. The puzzle deepened further after the launch of the James Webb Space Telescope in 2022. Webb's infrared instruments peered deeper into the early universe than previous observatories, revealing unexpectedly mature galactic structures only a few 100 million years after the Big Bang. In several cases, the central black holes appear disproportionately massive compared with the surrounding galaxies hosting them. The relationship seems inverted. Instead of galaxies forming first and black holes growing gradually afterward, some observations suggest black holes may have developed extremely rapidly, perhaps even helping organize early galaxy formation around themselves. No current theory explains everything cleanly. Perhaps unknown mechanisms allowed direct collapse black holes to emerge almost immediately after cosmic dawn. Perhaps early gas accretion operated far more efficiently under primordial conditions than it does today. Or perhaps entirely new physics influenced structure formation in the infant universe. Right now, astronomers do not know. This uncertainty has transformed early black hole research into one of the most active frontiers in observational cosmology. Each new distant quasar discovered forces theorists to reconsider how quickly complexity emerged after the Big Bang. The implications reach far beyond black holes themselves. For many years, scientists imagined the earliest universe as relatively simple, gradually assembling larger structures over immense spans of time. But the evidence now suggests that some of the universe's most massive and energetic objects appeared astonishingly early, almost immediately after the cosmic darkness began lifting. Black holes may not have arrived late in cosmic history. They may have helped shape the universe from the beginning. A black hole occupies almost none of its galaxy's total volume, and yet galaxies appear unable to grow without them. Astronomers discovered that the mass of a galaxy's central black hole correlates tightly with properties of the surrounding galactic bulge, particularly the random velocities of stars moving thousands of light years away from the center. The relationship persists across countless galaxies, despite the black hole directly dominating only a tiny central region. Something links their evolution together. The connection likely emerges through a process called active galactic nucleus feedback, usually shortened to AGN feedback. When matter falls toward a supermassive black hole, enormous amounts of gravitational energy convert into radiation, heat, magnetic fields, and particle jets before the material crosses the event horizon. The efficiency is extraordinary. Roughly 10% of the infalling matter's rest mass energy can be released outward during accretion. By comparison, nuclear fusion inside stars converts only about 0.7% of mass into energy. Black holes are far more efficient engines than stars. This released energy does not remain confined near the galactic center. Radiation pressure, high velocity winds, and relativistic jets push outward into the surrounding interstellar gas. Over time, These outflows heat the galaxy's cold gas reservoirs or eject them entirely into intergalactic space. Without cold gas, new stars cannot form. Galaxies gradually fade into quieter states populated mostly by old aging stars. Astronomers sometimes call these systems red and dead galaxies because they contain little ongoing star formation and glow primarily with cooler reddish starlight from ancient stellar populations. The leading explanation for their silence points back toward their black holes. As the central black hole grows larger and more active, AGN feedback intensifies until star formation becomes increasingly difficult across the entire galaxy. The black hole effectively regulates how many stars its galaxy can continue producing. This process reshapes cosmic structure over billions of years. Even our own galaxy participates in this larger evolution. Approximately 4.5 billion years from now, the Milky Way and the Andromeda Galaxy will begin merging. Their spiral structures will distort gradually as gravity rearranges hundreds of billions of stars across both systems. At their centers, two supermassive black holes will approach one another slowly. Simulations suggest the pair will eventually form a binary system orbiting within the merged galaxy's core. Over millions of years, gravitational interactions with surrounding stars and gas will drain orbital energy away until the black holes spiral inward and collide. The merger will release an enormous burst of gravitational waves. Long after humanity is gone, the distorted space-time from that collision will spread outward across the universe, carrying information about the final moments of two galactic centers becoming one. Black holes are not passive objects hiding inside galaxies. They influence star formation, redistribute matter and energy, regulate galactic growth, and help determine which structures survive across cosmic time. The shape of the observable universe, from giant elliptical galaxies to quiet stellar populations, carries the fingerprints of black holes written across it. A black hole feels permanent when measured against human history. Even mountains erode, oceans shift, stars explode and disappear, but black holes seem immune to ordinary change, surviving while entire galaxies transform around them. Yet Hawking radiation alters that picture quietly, relentlessly, across timescales so immense that language begins to lose meaning. Every black hole is slowly evaporating. The process is unimaginably gradual for large objects. A stellar black hole containing roughly 10 solar masses requires approximately 2 times 10 to the 67 years to evaporate completely. Sagittarius A star, with more than 4 million solar masses, would survive around 10 to the 87 years. Then there is Ton 618. Its evaporation timescale exceeds 10 to the 100 years, a number so enormous that ordinary comparisons fail completely. Writing the zeros alone becomes impractical. Entire cosmic eras unfold and vanish long before such a black hole notices any meaningful reduction in mass. For perspective, the universe today is about 1.38 times 10 to the 10th years old. The last normal stars are expected to exhaust their nuclear fuel after roughly 10 to the 14th years. White dwarfs will cool into black dwarfs. Neutron stars and planetary remnants will drift through increasingly empty galaxies. Over approximately 10 to the 39th years, even many stellar remnants may decay through quantum processes if proton decay occurs. Black holes outlive all of them. Eventually, the cosmos enters what physicists call the black hole era, a period when black holes become the dominant surviving structures in an otherwise dark and aging universe. No new stars ignite. Galaxies gradually dissolve through gravitational encounters. Matter thins into near emptiness, while black holes continue radiating almost imperceptibly into the darkness. But evaporation accelerates near the end. As a black hole loses mass, its temperature rises. Smaller black holes emit Hawking radiation more intensely, causing them to shrink increasingly quickly. During the final moments, the process becomes violent. In a fraction of a second, the remaining mass may convert into a burst of extremely energetic radiation comparable to millions of nuclear explosions released simultaneously. Then the black hole disappears completely. After the final evaporation events conclude, the universe enters an even quieter state. Only diffuse photons, electrons, positrons, neutrinos, and sparse low-energy particles remain scattered across expanding spacetime. Temperatures approach absolute zero asymptotically, while distances between particles continue increasing forever. No organized structures survive. The black hole era itself lasts incomprehensibly longer than all previous cosmic history combined. Compared with these future epochs, the entire age of stars, planets, galaxies, and biological life occupies only a brief, luminous interval near the beginning. We exist astonishingly early. Right now, the universe still contains warmth, structure, chemistry, gravity wells, and light crossing between galaxies. Black holes have not yet inherited the cosmos fully. Their era lies unimaginably far ahead, stretching across spans of time so vast that even the oldest galaxies become fleeting moments against the slow evaporation of gravity itself. Long before telescopes photographed black holes or detectors heard space-time tremble, this was the question hiding underneath the mathematics. What would actually happen to you? Not to a probe, not to a beam of light, to a conscious observer crossing the most extreme boundary in nature. After everything we have uncovered, the answer remains disturbingly incomplete, because modern physics itself separates into competing possibilities at the horizon. Under classical general relativity, the outcome is strangely calm. If the black hole is sufficiently massive, tidal forces near the event horizon remain weak enough that you would cross without immediate harm. Your body would float weightlessly, exactly as Einstein's equivalence principle predicts for any freely falling observer. No surface blocks your path. No physical marker announces the transition. You simply pass inward. Meanwhile, observers far away witness something entirely different. Because gravitational time dilation intensifies near the horizon, your image appears to slow continuously. Light leaving your body becomes increasingly redshifted, stretched toward longer wavelengths until it fades into darkness. To the outside universe, you never quite disappear. Your final moments remain suspended indefinitely at the edge. But from your own perspective, time behaves normally. You continue falling deeper toward the singularity, inside a supermassive black hole. That journey could last hours or even days of subjective experience before tidal forces finally become catastrophic. Communication outward becomes impossible immediately after crossing because every future path through space-time leads further inward. Escape ceases to exist as a physical option. Then came the firewall paradox. If the AMP's argument is correct, the event horizon cannot remain smooth. Instead, it becomes a lethal boundary saturated with high-energy quantum radiation. The moment you touch it, every atom in your body is destroyed instantly. There is no warning and no survival beyond the threshold. The equivalence principle fails completely at the horizon itself. Two theories collide there. General relativity predicts peaceful passage. Quantum mechanics appears to demand violent destruction. Both frameworks are extraordinarily successful everywhere else in nature. Yet inside black holes, they refuse to coexist cleanly. But there may be another possibility. Quantum gravity models suggest the singularity itself could be replaced by unknown Planck scale physics, regions where spacetime becomes quantized, discrete, or fundamentally altered. In some proposals, collapse halts before infinite density forms. In others, information reemerges through mechanisms we do not yet understand mathematically. What happens to you there? We genuinely do not know. The strangest possibility may be black hole complementarity. In that framework, two contradictory descriptions coexist simultaneously. An outside observer sees you destroyed at the horizon, your information smeared across its surface and eventually released through Hawking radiation. Yet, from your own viewpoint, you cross normally and continue inward toward the black hole's interior. Both accounts remain internally consistent. No observer can compare both realities directly, so no contradiction becomes experimentally visible. At this depth, the universe may no longer provide a single, objective narrative shared by everyone. The question of survival itself may depend entirely on where and how reality is observed. Before radio telescopes stretched across continents and detectors listened for distortions smaller than atomic nuclei, black holes existed only as consequences hidden inside equations. We discovered them indirectly. Again and again, the universe has revealed its deepest structures not through visibility, but through influence. We do not see black holes themselves. We watch stars whip around empty regions of space at impossible speeds. We measure gas heating to millions of degrees while spiraling inward. We detect gravitational waves crossing billions of light years, carrying the signature of collisions between invisible objects. The absence leaves fingerprints. Dark matter follows the same pattern. Galaxies rotate too quickly for their visible matter alone to hold together, implying the presence of unseen mass surrounding them. Gravitational lensing, the bending of light by gravity, maps this hidden structure across galaxy clusters like transparent scaffolding. Nearly 27% of the universe appears to consist of something no telescope has ever directly observed. Yet its gravity remains undeniable. Even the oldest light we can study arrives indirectly. The cosmic microwave background began as brilliant plasma radiation roughly 380,000 years after the Big Bang, when the early universe cooled enough for atoms to form and light to travel freely. Over 13.8 billion years of cosmic expansion, those wavelengths stretched into faint microwaves, now filling every direction in space. We cannot see the beginning itself. We see its afterglow. This pattern repeats throughout modern physics. The most important discoveries often emerge not from observing an object directly, but from understanding how reality rearranges itself around something hidden. We build models, test predictions, and compare them against traces left behind in measurable phenomena. Black holes became the ultimate example. The famous image of M 87 times in 2019 did not photograph a black hole in the ordinary sense. The dark central region emitted no light at all. The glowing ring surrounding it consisted of superheated plasma orbiting at relativistic speeds, organized into structure by gravity near the event horizon. Years of radio wave observations from observatories across Earth were combined through interferometry, a method that merges distant telescopes into one virtual instrument. The image was reconstructed mathematically. What we finally saw was absence outlined by its consequences. But that has always been how science progresses. Electrons cannot be observed directly with the naked eye. Quarks remain permanently confined inside larger particles. Quantum fields, space-time curvature, and dark energy are known through effects, not visibility. Physics advances by identifying patterns stable enough to reveal hidden rules operating underneath the surface of experience. Black holes sharpened this method to its limit. Inside their horizons, our current laws cease agreeing with one another. General relativity predicts one outcome, quantum mechanics predicts another. Between them lies a region we still cannot describe coherently. Yet, even there, we continue learning by studying distortions carried outward into the observable universe. Sometimes the clearest understanding comes not from what the cosmos reveals openly, but from what it refuses to let us see. A black hole begins as an astrophysical object, collapsing stars, curved spacetime, extreme gravity. But eventually, the discussion changes shape, because hidden underneath the equations is a quieter question about memory itself. Can the universe forget? Quantum mechanics says no. According to the mathematical structure underlying the theory, information is conserved. Every interaction between particles transforms the universe from one quantum state into another without erasing the previous state's underlying information. In principle, if you possessed complete knowledge of every particle involved, the process could be reversed mathematically. Nothing vanishes completely. When paper burns, the smoke, ash, heat, and scattered photons still contain the information necessary to describe what once existed. Recovering it in practice would be impossibly difficult, but the laws themselves permit it. Quantum theory treats the universe as a system that evolves without deleting its own history. Black holes disrupted that assumption. Matter falls inward, carrying information about every particle configuration, every quantum state, every microscopic detail. But Hawking radiation appears random. It contains temperature and energy, yet no obvious record of what entered the black hole originally. If evaporation finishes completely, the information seems gone forever. Not hidden, destroyed. That possibility deeply unsettled physicists because quantum mechanics depends on information conservation at its foundation. Without it, the predictive structure of the theory begins breaking apart. Probabilities stop evolving consistently. Cause and effect lose mathematical continuity across time. But the discomfort was never emotional. It was structural. The equations governing microscopic reality appear to require a universe that preserves its records absolutely, even when those records become inaccessible. Black holes threaten to introduce permanent gaps into physical law, regions where history itself dissolves beyond recovery. The holographic principle emerged partly from this crisis. Inspired by black hole thermodynamics, physicists such as Gerard Hooft and Leonard Susskind proposed that all information contained within a volume of space might actually be encoded on its boundary surface, much like a hologram stores three-dimensional information across a two-dimensional sheet. Inside and surface become equivalent descriptions. For black holes, this suggests that information never truly disappears behind the event horizon. Instead, it remains imprinted across the horizon itself, gradually leaking outward through Hawking radiation over incomprehensibly long timescales. The black hole behaves less like a cosmic shredder and more like an extraordinarily slow encoder. But the implications reach far beyond black holes. If the holographic principle reflects something fundamental, then space-time itself may not be the deepest layer of reality. Distance, geometry, gravity, perhaps even time, could emerge from underlying informational relationships operating beneath what we perceive as physical existence. Matter would not create information. Information would create matter. Black holes forced physics into this possibility because they pushed our theories past their comfortable limits. At the horizon, gravity, thermodynamics, quantum theory, and geometry become inseparable. The paradox revealed that reality may not ultimately be built from objects moving through space, but from patterns of information woven together into the appearance of a universe. A falling apple once suggested that gravity pulls objects together across empty space. That picture survived for centuries because it matched ordinary experience so well. But black holes forced physics beyond ordinary experience into conditions where the deeper structure underneath reality became impossible to ignore. Einstein changed the question entirely. Gravity, according to general relativity, is not a force acting through space. It is the shape of spacetime itself. Mass and energy distort the geometry around them, and objects simply follow the straightest possible paths through that curved geometry. Matter tells spacetime how to bend. Spacetime tells matter how to move. Planets orbit stars because spacetime near stars is curved. The Earth is not being pulled sideways around the Sun by an invisible force. It is moving through warped geometry the way a marble rolls across a curved surface. Black holes represent the most extreme version of that curvature ever discovered, regions where space-time bends so intensely that all outward paths collapse inward. Geometry becomes destiny. This reshaped our understanding of time as well. Before relativity, time was assumed to flow uniformly everywhere, a universal clock shared equally across the cosmos. But Einstein revealed that time depends on motion and gravity. Clocks in stronger gravitational fields tick more slowly relative to clocks farther away. The effect is measurable even on Earth. Atomic clocks placed aboard airplanes drift slightly relative to identical clocks on the ground. GPS satellites, orbiting thousands of kilometers above Earth, must constantly correct for relativistic time differences, or navigation systems would fail within days. The top of a mountain ages faster than the valley below it, though only by tiny fractions of a second across a human lifetime. Every mass reshapes time locally. Black holes extend this principle to its absolute limit. Near the event horizon, space-time becomes so distorted that the normal structure separating space from time begins to break apart. Outside the horizon, you may choose different directions through space, but you continue moving inevitably forward through time. Inside the horizon, those roles reverse. The singularity becomes part of your future in the same unavoidable way tomorrow normally is. You cannot decide not to move toward it because all possible futures point there automatically. The geometry itself permits no alternative path. But this raises a deeper problem. If time bends, slows, stretches, and changes relative to gravity, then what exactly is it? Is time a physical dimension, like length and width? Is it an emergent consequence of entropy, the gradual increase of disorder throughout the universe? Or is it something even more fundamental, woven directly into the architecture of reality in ways we still do not understand? Physics has no final answer. Quantum mechanics treats time differently from general relativity. Thermodynamics introduces another interpretation entirely. Cosmology ties time to the expansion of the universe itself. Black holes sit precisely where all these descriptions collide, forcing us to confront the possibility that our most familiar experience, the steady passage of moments, may emerge from laws far stranger than intuition allows. Long before Earth formed oceans or living cells, earlier stars were already burning through their nuclear fuel, across the young Milky Way. Inside those stars, lighter elements fused into heavier ones under immense pressure and temperature, building the raw material from which planets, atmospheres, and eventually biology would emerge. Your body carries that history quietly. Carbon formed in stellar cores through the triple alpha process, where three helium nuclei fused together under extreme conditions. Oxygen followed, nitrogen, silicon, iron. Many of the atoms moving through your bloodstream tonight were forged billions of years ago, inside stars far more massive than the Sunday. Some of those stars died violently. When extremely massive stars exhausted their fuel, gravity overwhelmed the outward pressure supporting them. Their cores collapsed. Supernova explosions scattered heavy elements across interstellar space, and in certain cases, the remnants continued collapsing into black holes. The stellar black holes, now drifting invisibly through our galaxy, are connected directly to the same generation of stars that chemically enriched the clouds from which Earth eventually formed. Life emerged from their aftermath, but black holes may participate in cosmic recycling more deeply than we first imagined. Hawking radiation suggests that black holes are not permanent prisons isolating matter forever from the rest of existence. Instead, they slowly lose mass over unimaginable spans of time, releasing energy outward particle by particle. Information may survive the process. If the information paradox resolves through holography or some future theory of quantum gravity, then matter entering a black hole is not erased completely. Its information becomes transformed, scrambled across the event horizon, and gradually re-emitted through subtle quantum processes. The black hole does not simply consume, it processes, encodes, and redistributes. Nothing disappears absolutely. This idea connects unexpectedly with thermodynamics. In the 1970s, Jacob Bekenstein and Stephen Hawking discovered that black holes possess entropy, the physical quantity associated with disorder and information content. Remarkably, a black hole's entropy is proportional not to its volume, but to the surface area of its event horizon. That relationship changed theoretical physics permanently. The formula suggested a hidden connection between gravity, information, quantum theory, and thermodynamics that physicists still do not fully understand. Somehow, space-time geometry itself appears tied to informational structure at the deepest level. But black holes also reveal another boundary. Everything we know about them comes from outside observation. We infer interiors mathematically, yet no information can return directly across the event horizon for external verification. The inner experience of crossing remains inaccessible to the rest of the universe. Two observers become permanently separated by the structure of space-time itself. This is not poetic language. It is literal physics. Certain aspects of reality can only be experienced from within a particular frame of reference, never fully translated outward into complete external description. Black holes make this limitation unavoidable. They expose a universe where observation always has boundaries, where perspective changes physical description, and where some regions of existence remain fundamentally private even within the laws of nature themselves. A telescope extends human sight. A detector extends human hearing. Mathematics extends human reasoning beyond intuition itself. For centuries, science advanced with the quiet assumption that enough observation and enough intelligence could eventually illuminate every corner of reality. Black holes complicated that assumption. The event horizon is not merely a boundary surrounding matter and light. It is a limit built directly into causality, the structure determining which events can influence other events across spacetime. Once something crosses the horizon, no signal carrying information about it can return outward faster than light. The interior becomes permanently inaccessible to outside observers. Knowledge itself acquires geometry. This realization reaches far beyond black holes. Cosmology reveals that our observable universe also possesses a horizon, though created not by gravity alone, but by cosmic expansion. Space itself has stretched for 13.8 billion years since the Big Bang, and distant regions now recede from us so rapidly that their light will never arrive, no matter how long the universe continues existing. There are galaxies forever unreachable. The observable universe spans roughly 46.5 billion light years in every direction, yet this immense sphere is not the entire cosmos. It is simply the portion from which light has had enough time to reach us since cosmic expansion began. Beyond that horizon may exist vastly more structure, perhaps infinite in extent, permanently disconnected from observation. We inhabit a bubble of knowability. In this sense, our cosmological horizon resembles an event horizon structurally. Both divide spacetime into regions that can exchange information and regions that cannot. The laws of physics may continue normally beyond those boundaries, but direct observation becomes impossible in principle. Existence exceeds accessibility. That distinction matters profoundly. Scientific realism, the idea that reality exists independently of observation, survives comfortably with hidden regions. Physicists do not conclude that black hole interiors vanish merely because we cannot inspect them externally. Likewise, cosmologists do not assume the universe ends at the edge of observability. But black holes forced a deeper recognition. There may be truths about reality that no experiment can ever recover because the universe itself prevents the necessary information from reaching us. The limitation is not technological weakness. It is embedded directly into spacetime geometry and the finite speed of causal influence. Some questions may possess no observable answer. This possibility reshapes the philosophy of science quietly but fundamentally. Traditionally, unanswered problems suggested missing knowledge awaiting future discovery. Black holes introduced another category entirely, phenomena whose complete internal description may remain forever inaccessible to any external observer, regardless of intelligence, instrumentation, or time. The boundary is physical. Even mathematics encounters tension there. Quantum theory demands information preservation. General relativity permits hidden interiors. Cosmology imposes horizons beyond causal contact. Together, they describe a universe where reality extends beyond what any observer can fully access from a single location within spacetime. But perhaps this has always been true. Every conscious being experiences existence from inside a limited frame of reference, seeing only a partial cross-section of reality at any moment. Black holes simply made the limitation explicit, turning the edge of knowledge from an abstract philosophical concern into a measurable feature written into the architecture of the cosmos itself. Long before the first human looked upward, Sagittarius A times already waited at the center of the Milky Way, 4.15 million solar masses hidden behind dust, silence, and distance. Our solar system has completed only about 20 orbits around the galaxy since its formation 4.6 billion years ago. Through all of that time, the black hole remained, unseen, unbothered. We live 26,000 light years from it, on a small rocky planet orbiting an ordinary star among hundreds of billions of others. Nothing about our position appears central or permanent. The cosmos does not arrange itself around human scale, human lifespan, or human understanding. But we emerged here anyway. The universe is approximately 13.8 billion years old. Complex multicellular life on Earth has existed for perhaps 600 million years. Homo sapiens appeared roughly 300,000 years ago. Recorded history occupies only a tiny fraction of that already narrow interval. Our chapter is brief. Ahead lies a future vastly longer than the past behind us. In roughly 5 billion years, the sun will exhaust its hydrogen and expand into a red giant. Trillions of years later, star formation across the universe will cease as interstellar gas is exhausted. Galaxies will darken gradually. White dwarfs, neutron stars, and black holes will dominate the remaining structure of the cosmos. Then comes the black hole era. For spans exceeding 10 to the 100th years, black holes will outlast nearly everything else. They will drift through an increasingly cold and empty universe, slowly evaporating through Hawking radiation while space-time itself continues expanding into darkness. Eventually, even the largest among them, objects like TON 618, will disappear in brief final flashes of energy. Afterward, silence deepens further. No planets will remain to orbit dead stars. No biological eyes will watch the last radiation fade. No memory will survive to record that black holes ever existed at all. Entropy, the gradual spreading of usable energy into disorder, will continue its slow movement toward thermal equilibrium across the cosmos. And yet we exist astonishingly early in this timeline. We inhabit one of the few eras when stars still shine brightly, heavy elements still circulate through galaxies, and chemistry still permits oceans, atmospheres, cells, brains, and questions. The conditions allowing conscious observers may occupy only a thin, luminous band between cosmic beginning and cosmic exhaustion. Black holes sharpen that realization. They do not care whether we solve their paradoxes. The event horizon does not pause for human intuition. Singularities do not require our mathematics to remain consistent. The universe operates according to principles deeper than preference, comfort, or comprehension. But within that universe, matter became conscious. Atoms forged inside ancient stars assembled into nervous systems capable of wondering what lies beyond an event horizon and why space-time bends around mass. Somewhere between the birth of galaxies and the evaporation of black holes, the cosmos produced beings able to examine the darkness and ask what it means. Perhaps that is enough. Not certainty, not mastery, just awareness. A brief moment in cosmic history when the universe, through us, became capable of observing itself before the lights eventually fade and the long future continues outward into the quiet.